Hello viewers, welcome back to our series of lectures on spectroscopy. And today we will continue our discussion on electronic spectroscopy, and this concluding part on electronic spectroscopy we will focus attention on the Frank quantum principle, the dissociation energy and things like that. The session is planned as follows, that is, to begin with we will briefly review the contents of the previous sessions. Thereafter we will talk about the basic premise of determining the intensity of electronic spectral lines, and in this context we will bring in the Frank quantum principle. Then we will see that how does this principle help us to predict the nature of spectrum obtained in different kind of molecules. Thereafter we will talk about the concept of dissociation energy, and we will see that how do we determine this dissociation energy by using electronic spectrum. Thereafter we will briefly recall the kind of molecular orbitals, the sigma, pi and non-bonding molecular orbitals, and then we will see that what kind of transitions are observed in case of molecules. Then towards the end we will sum up what we do in today's session. So let us make a beginning by recalling what we did in the previous session. In the previous session we basically started by defining what is electronic spectroscopy. Thereafter we explained the potential energy curves for diatomic molecules, wherein we saw that they are the electron energy levels there, and then we stated the selection rules for the transition amongst the electronic states for diatomic molecules. Having done that, we moved on to a very important approximation, what is called as the Born-Oppenheimer approximation, and then we saw that in the light of Born-Oppenheimer approximation, how do we describe the energy level diagram under this approximation. Thereafter we discussed the origin of vibration, core structure and the kind of information which is available from this. That means we talked about the vibrational progressions and things like that. So with that being done in the previous session, let us continue and then see that today, since we want to talk about the intensity of the spectral lines here, let us quickly recall what we did in the introductory session on electron spectroscopy or the spectroscopy per se, that we talked about intensities of spectral lines, and therein we realized that now suppose we have got two systems here, say molecule A and molecule B, and let us take the transition say from level A1 to level A2 in molecule A and from level B1 to B2 in molecule B. I am just taking an example here, and let us assume that delta EA is equal to delta EB. That means the difference in energy levels for the molecule A and for molecule B happen to be same. We are assuming it to be so, and also we assume that we take the same concentrations of the two molecules there. And then if I take the spectra and find that the absorbance of A, that means the intensity of the signal which is obtained for molecule A happens to be more than B, then the only reason for that can be that the transition probabilities are different. That means the transition probability for molecule A is more than that of the molecule B, then only the intensity can be more there. So transition probability is the concept which lets us know about the intensities of spectral lines there. Also, if you remember that in the introductory session on spectroscopy, we talked about that the transition probability actually has got two terms there. The term 1, term 2, I am not quantifying, I am not trying to give any expressions for that, I want to just give a qualitative aspect of this, and the term 1 basically determines the selection rules which we had talked about in the previous session, and the term 2 is the one which determines the intensity. And as I just mentioned, term 1 has been discussed, that means the selection rules has been discussed in the previous session, and today we will talk about the Frank quantum principle, which actually is very important in determining the intensity in case of electronic spectral lines there. Let us see what is this Frank quantum principle here. The Frank quantum principle is very straightforward. Let us first read it here. It says that according to Frank quantum principle, the electronic transitions occur so rapidly that the nuclear positions do not change during the transition. What does it mean is this? We know that there is no molecule which is stationary. Any molecule is undergoing some kind of a vibration. Let me take a diatomic molecule. If it is undergoing vibration, it has got electronic round around this, and if I give a photon, and I am talking about electronic excitation, that means this electron will go from level 1 to level 2, and what this principle tells us is that this transition is so fast that this vibrating molecule is not able to change its position in the time taken by this electron to get excited over there. That means the implications will just come down to that. In other words, we can say that the time taken for the electron excitation is very short as compared to the time for a vibration, because vibration motion is not very fast, electronic excitation is much faster. So that is what is basically called as the Frank quantum principle. Now the implication of that is that the electronic transition can be represented in terms of vertical lines. This is my electronic ground state here for the molecule here. This is electronic excited state here. Now when I say that I am giving a photon to that, the electron goes from level 1 to level 2. This is my electronic excitation, and it happens so very fast that the vibrating molecule is not able to change its position that fast. So the consequence of that is we can represent this transition in terms of vertical lines. That means if a transition starting from here, it will lead to this place here. That means by the time the transition takes place, the internuclear distance does not change. So that is the implication of Frank quantum principle. To understand that, we have to just quickly recall one more aspect of the vibrational wave functions in case of electronic states there. We know that when we talked about electronic transitions there, this is my typical Morse potential curve over here for a electronic energy level over here, and these are my different vibration energy levels over there. So this is V is equal to 0, V is equal to 1, 2, 3 and so on and so forth. Why I am talking about this is that this potential curve over here essentially refers to this. That means if I have got a diatomic molecule, I am keeping one atom fixed and second atom I am trying to make it undergo vibration there. So when this undergoes vibration, what happens to energy? That is given by this Morse curve there. Now what is important here is that if I look at, classically speaking, if I keep this atom fixed and taking this atom there, so if I look at here, say this is my equilibrium position for the molecule. The molecule is expanding, coming back, contracting and so on and so forth. If I look at classically, essentially what I expect is that I am just holding this as fixed there. So the time spent by this second atom here will be more towards the extremities here. That means in principle from classical mechanics, I expect that it should spend more time over here and here rather in the middle. But what you find is the curves shown over here are the outcome of quantum mechanical treatment of vibration here. So we find that, say for V is equal to 0 level, we find the probability is maximum to be here, and for V is equal to 1 level, this is the probability curve there. That means the probability is maximum at 1 by 4 and 3 by 4 and so on and so forth. So what you find is, as the vibration energy level increases, we find that the behavior becomes more classical there, because see there, so at V is equal to 4 level, the molecule is spending more time here and here rather than in the middle here, whereas in case of V is equal to 0, it spends most of the time in the middle over here. So that is the basic contrast between classical and quantum behavior, and what you find is that in the limits of V is equal to a large value, the quantum mechanical behavior tends to become classical in nature. Because this curve is very important for us to go further a little. Let us see. This is my wave functions over there. Now, as a consequence of Frank quantum principle, what we see is that the transition takes place with high probability. What is required is that there must be a large overlap between the vibration states in the initial and final electronic states there. That means this is my initial electronic state, this is my final electronic state. So if the transition happens in such a way, that is the wave function here and here happen to be similar, that means there is a good overlap there, then transition probability will be more, and that means the electron transition will occur to vibration energy level which resembles most closely to the vibration level in the ground state here. That means, say from here to here the transition has to take place. So probably this transition as shown here is more significant rather than a transition to something of this kind here. Let us take another example here. So this picture is very clear. In this picture what you show is that this is my electronic ground state here, and these are the corresponding vibrational energy levels there. This is my electronic excited state and the corresponding vibration energy levels here, and I am showing you two transitions here. The blue one is transition A. You find is it is from the center of this, that means a peak of this vibration energy level here, and it is landing onto the corner part over here, very less probable here. And whereas the second transition here, the transition B, is starting again from the similar position, but it is landing up into a situation wherein there is a maximum over here. So between the two transitions, what you will find is, as per the Frank quantum principle and the two things I just talked about, that is the overlap between the vibration energy levels in the ground state and excited state must be as significant as possible. We find that transition A is from vibration level from maximum probability to a minimum probability region there. So this is not very effective. whereas for transition B, it involves two vibrations of similar probability. Here it is the maxima here, so is here. So this transition is going to be more effective, more probable, more intense. So that is the meaning of the Frank quantum principle, the significance of Frank quantum principle in terms of we are giving transitions as vertical lines there. And secondly, there are two more things very important is that what kind of levels are going to give me more probability there. Okay. Now, then let us go a little further and recall from our previous session, we saw that the possible vibrational transitions in electronic states are like this. That means you got this is my electronic ground state and there is the corresponding vibration energy levels there. This is my electronic excited state and the corresponding vibration energy levels here. And we find that as per the selection rule, there is no restriction on any change in the delta V value. That means it can go from any vibration energy level to another one there. But typically what happens is most of our transitions will originate from V is equal to 0 level there. V rho prime is equal to 0, this is my V prime level there. So from all these transitions will be leading to some kind of what's called as a nu prime or V prime progression here. And that is how typically a spectrum looks like. That is all we discussed in the previous session. This particular thing we discussed in detail in the previous session here. So what I want to recall here is that is the possible vibrational transitions in electronic states kind of accompanying electronic excitation lead to a V prime progression which looks something like this. That means it gives me a series of lines there, or you generate a band. That is a typical electronic spectrum as it looks like. Let us go further and see that how do I use the Frank quantum principle to determine the nature of vibration progression, because that nature of vibration progression it essentially means is where are the signals coming and what is the intensity pattern there. Actually that depends on the relative disposition of the potential energy curves for the two electronic states. That means, and there are three possibilities there. The first one happens to be that is the internuclear distances are equal in the upper and the lower states. That is one possibility. Second possibility is that in the upper state the internuclear distance happens to be little larger than the lower state. And the third possibility is that upper state internuclear distance happens to be considerably greater than that in the lower state there. We will just do each one of them. Let us see, let us take the first case. The first case is when Re prime is equal to Re double prime. Re prime is the equilibrium distance in the excited state and Re double prime happens to be that in the lower state, the ground state here. That is how the energy level diagram will look like. So we find that this is my electronic ground state, that is E double prime here, this is E prime. In this E double prime state, we find that this is my typical internuclear distance here. And we find that it happens to be roughly the same in the excited state. If this be so, what kind of spectra do I get? As discussed before, we know that in all such transitions, the transitions will originate from V double prime equal to 0 level here. So if they start from here, there will be somewhere maxima here in the center here, from there it will originate and go up there. So you find that if I just draw a vertical line here, it will land into V prime is equal to 0 level there, because the two distances, the internuclear distances are similar there, and this will be the most intense signal there. That the spectrum will be something like this. The 0-0 transition will be the most intense one, and a transition which originates from say somewhere in the neighborhood here, say somewhere here, if it goes vertically up, it will land into V is equal to 1 level or further up 2 level and so on and so forth. So you find that as they go into higher energy levels there, the intensity pattern will become like this. That means 0-0 will be the most intense one, 1-0 will be lesser intense, 2-0 will be still lesser and so on and so forth. So that will be a typical pattern what will be observed in this kind of a disposition of the two energy levels there. That means if Re prime is comparable to Re double prime, then that is a kind of spectrum I am expecting here. Now let us take the second case, case B, wherein Re prime is greater than Re double prime. That is, we have the two energy levels as follows. This is my double prime level, this is my prime level here. So in this prime level, the equilibrium distance is more than that in the ground state here. So in this case, as per the Frank quantum principle, as before, my transition will originate from in the center of this, that is a maxima here. It will go up there, we find that it will land up somewhere here, say V is equal to 2 level here. And any transition which goes from somewhere here, it may be landed into 1 or to 0, and from this side which they originate, they will go to higher levels there. The spectrum will look something like this. That is, the most intense line will be when is equal to 2-0 line there. That means from V double prime is equal to 0 to V prime is equal to 2 level, as per this particular diagram shown over here. So 1 0 will be lesser intense, 0 0 will be still lesser intense there. Same will be true of 3 0, 4 0 and 5 0 and so on and so forth there. So that is a typical kind of a spectrum I will be observing in this case here. If it so happens that Re double prime happens to be more than Re prime, that means we have got this happens to be shifted this side and this happens to be like this. So in that case also we get a similar kind of a pattern there that we can do on your own. Let us go to the third case now, wherein Re prime is far greater than Re double prime. That means the excited state, the equilibrium distance is much larger than the greater of the ground state. That is, we have got this kind of a situation. Now in this case we find that this is Re prime is much larger than Re double prime here. So in this case the most intense transition will occur from say 0 level, it will lead maybe somewhere here, and the transition which will originate from somewhere around this place, they will land into say V is equal to 3 level here, 2, 1 or whatever, and the ones which will be originating from the left hand side of this most intense transition, they will land into the region where there is no stability here, and the spectrum will look something like this. That is, the most intense transition will be somewhere here. It may be into a region of continuum or maybe into a bound state there. But typically the spectrum will be something like this. That means we will have series of lines here, and after certain stage, because what you find is any transition which is landing up somewhere, because this is the maxima here, any transition which lands over here will lead into the breakdown of the molecule there. The molecule is not stable thereafter. So the molecule will break down into the components there. Since they break down into components, I will not get a signal there, I will get a continuum there, because that energy is not quantized anymore thereafter. So that is the kind of spectrum I will be getting there. Okay. Now having done this, so these are the three possibilities as regards the relative disposition of the energy levels and the corresponding the spectrum obtained in the cases there. Now let us look at one more concept of the dissociation energy of diatomic molecules, and that is how do we talk about it here. This is my typical most potential curve there. Now we know that typically the most of the molecules will be in the V is equal to 0 state. This is the 0 point energy there, and if I give energy to the molecule gets excited to V is equal to 1, 2 and so on and so forth. So this is the limiting value here, so it is called as a V max here. That means if I give energy greater than that can take the molecule from V is equal to 0 to V max, beyond this the molecule will break down there. So this limiting value from say V max level to that of the V is equal to 0 level is called as the dissociation energy of the molecule there. And if I want to talk about D equilibrium, that is from here it starts, say from 0 energy here to this. Typically we will be talking about the D naught here. D naught is the dissociation energy of the molecule, which basically happens to be the difference in the energy of the V max level and that of the V is equal to 0 level there. Now the issue is, how do I find out dissociation energy from electronic spectrum? Let us understand that. Let us take up different cases there. I will take up 3 cases here and see that how do I determine the dissociation energy. Let us take the first case when the excited state happens to be a stable excited state here. Now what happens? That means we got the relative disposition of the two energy levels as this, and this is my ground state, the excited state there. Now in this case the spectrum will be something like this, we just discussed 2 minutes back. That is, the spectrum will be made up of certain lines there, and then there will be a region of continuum there. That means there is no kind of discrete lines there. Let us imagine you have got a molecule in the vibrational ground state of electronic ground state. I give electronic energy to this, the molecule gets excited to state there, and then thereafter it breaks down. It breaks down, and then suppose I give energy just sufficient such that the energy of the photon which I give happens to be equal to D naught double prime, that is the dissociation energy in this ground level there, plus E excitation here. So if I give energy just like this, so what will happen? The starting point will be my diatomic molecule, and the end will be the 2 atoms there or at their ground states there. That means they are not having any kinetic energy over there. That is, if I just try to work out that this energy, this limit here, the continuum limit essentially will correspond to the total energy from double prime is equal to 0 level to the V max level of this one here. That means essentially this line here, the origin of the continuum corresponds to this energy, that is D naught double prime plus E excitation. E excitation is the excitation energy of the fragments of the molecule there. if I have got this, that means the molecule has dissociated and the fragments have got no kinetic energy. That is my assumption here. If that be so, then I can say that nu prime, the continuum limit as I just mentioned, will be equal to d naught double prime, that is the dissociation energy in the ground state, plus E excitation of the fragments there. Now the question is that I have got only one data, that is I got only nu prime continuum, but there are two things which I have to find out. I do not know this, I also do not know this, but I want to find out this one here. So if I know E excitation somehow, then I can find this value, and if I know this somehow, I can find this value here. And what we do is, since I want to make a good estimate of d naught double prime, what do? The strategy is as follows, that is, I get an estimated value of d naught double prime from thermodynamics. That means I do it thermodynamical experiment there and try to find out some measure of d naught double prime. Thereafter, once I know d naught double prime, essentially my data from electronic spectrum is that continuum limit, that is equal to d naught double prime plus E excitation. So there are two terms there. I do not know both the terms individually. This is my data, that is only one data I have got with me from the spectrum. So what do? I somehow get the value of d naught double prime from thermodynamics, some estimate of this. Okay. So I know this well, I know it accurately, I know this approximately. So from this minus this, I can get some kind of estimate of my E excitation of the fragments there. Then what do? I look into the excitation spectrum of the fragments and find out what particular signal kind of best matches with this estimate of mine of E excitation. Once I know this estimate, because mind you the spectrum will be very accurate values will be there. Thermodynamic values may be having some kind of a approximation in that case. So from once I know the value of E excitation from the electronic from the excitation spectrum here, I substitute back here, then I get the value of d naught double prime. That is the strategy over here. That is, I substitute the value of E excitation which I obtained from the absorption spectrum of the fragments there, and then I get the value of the dissociation energy there. Let us take the second case where the excited state happens to be unstable. So in this case what happens? So that is the kind of energy level diagram we have. This is my ground state which is stable. This is excited state which is unstable. That means this unbound state. The molecule is not stable in the state at all. So in this case the spectrum will be something like this. In the previous case we had set of discrete lines followed by continuum. In this case, no matter what I do, any excitation will lead to the breakdown of molecule there. That means the spectrum will be just a continuum there. I will not get discrete lines in this case. And here again, this, if I can somehow locate this starting line there, that means if I give energy to be equal to d naught double prime plus E excitation, so that is somewhere here. That means if I give energy equal to from this level to this level, then what I will be getting? My starting molecule is, say, molecule AB. If you give this energy, I will get A plus B. So that is the meaning of this, because that is the molecule has undergone dissociation. It has broken down into A and B individually. Now suppose I give energy more than this. If I give energy, say, as shown by this particular line here, if I give this much energy there, then what will happen? I will get the two atoms here, A and B, and also this extra energy will come out as the kinetic energy of either component A or B or A and B put together. So that is how the energy will be conserved in that. So here again, what do? That is, the excited state, as I mentioned, is not bound. That means the molecule dissociates as soon as it gets excited there. That means you just give energy, molecule dissociates, and the products have got energy equal to E excitation if there is no kinetic energy, and thereafter the spectrum will be a continuous spectrum. There is a continuum there. So from the lower limit of that, I can find out d naught double prime as we did in the previous case there. Now let us take up the third case here, that is when there is no continuum limit. So in this case, how do we find out the value of dissociation energy there? In this case, actually we make use of the fact that the vibration energy levels or vibration lines, they get converged there. As delta V value increases, the lines get closer and closer. You would have seen that in the spectrum there. So this fact actually is made use of, and we know from our understanding of vibration spectroscopy that the vibration energy level is given by the following expression there, where V happens to be the vibrational quantum number there. And if I find out the expression for delta E happens to be, that is, energy of V plus 1 level minus energy of the Vth level. If I just substitute that and work out, this comes out to be the following expression there, where Xe happens to be the inharmonicity constant there, and V is the vibration quantum number. And essentially, as I just said, that as this increases, the lines gets closer and closer. A limit will come when the two lines are just continuous. That's called as a limit there. So when that happens, we can say that the delta E value becomes 0. When it tends to be 0, we then substitute this delta E expression to be equal to 0 here. When I do that and rearrange it a little, we find that we get V max to be equal to 1 by 2 XE minus 1. That means this gives me an estimate of the V max level. That level, thereafter there will be dissociation there. So we know that our dissociation energy happens to be the energy of V max level minus V is equal to 0 level there. So if I know somehow the value of V max, I get the energy of that level, V0 energy I know of, I take the differential true, I get the dissociation energy. So that is how we manage to get the dissociation energy from this kind of spectra as well. Okay, let's move further and quickly recall a few things which we need to bring in here. This we can recall from our understanding of chemical bonding, and even in quantum mechanics we did talk something about molecular orbital theory. Let's quickly recall that what kind of energy levels do we get here. Now typically what I want to bring home here is, because we have done that earlier, so I will quickly just recall that I will recall it from the diatomic molecules. That is, in case of diatomic molecules, the atomic orbitals or the constituent atoms, they combine together to generate molecular orbitals, and these molecular orbitals are spread over the whole molecule. We all know that. And then we also know that the overlapping of atomic orbitals along the bond axis gives sigma orbitals, and which are any overlapping which is lateral ones, they give us the pi orbitals. We know that all. Let us see in pictures. We know that the two s orbitals will combine. S orbitals are spherical, they combine together to give me a sigma bonding orbital or an anti-bonding orbital there. Both of them are sigma there. Similarly, if I take 2p-z orbitals to combine together, so this is my 2p-z here. So when they combine, they will give rise to a bonding orbital there. This will be an anti-bonding, and both of them again will be sigma orbitals, because any overlap along the internuclear axis is going to give me sigma molecular orbitals there. Second kind of orbitals, the molecular orbitals what we get as a consequence of LCAO, that is linear combination of atomic orbitals, are called as pi molecular orbitals. They originate when the orbitals overlap laterally. That means these are two, say px orbitals or two py orbitals. When they combine, they give rise to a pi molecular orbitals. If the constructive overlapping is there, if there is a destructive overlapping, I get an anti-bonding orbital there. Both of them are pi orbitals there. So the basic premise is we got two kinds of orbitals: sigma when the overlapping is along the internuclear axis, pi if the overlapping is lateral or sideways. And there is a third kind of molecular orbital, what is basically called as the non-bonding molecular orbital. Let us understand that. Let us take the example of, say, hydrogen fluoride. In case of HF molecule, what happens is there is 1s orbital of hydrogen and 2s orbital of fluorine and 2pz orbital of fluorine again. So all these two are spherical here. This is along the z axis there, so internuclear axis. These three orbitals combine together to give me 3 sigma orbitals there, 1 sigma, 2 sigma and 3 sigma. And these px and py orbitals on the fluorine atom, they do not participate in the molecular orbital formation there, because they have a different symmetry. They are not along the internuclear axis there. So these orbitals stay as such, because they are the part of the fluorine atom here. This is a part of the HF molecule there. So these such orbitals are called as non-bonding molecular orbitals. Essentially, the point I want to bring home is that in any molecule, if you look at, there are three kinds of molecular orbitals: sigma molecular orbitals, pi molecular orbitals and non-bonding molecular orbitals there. And if I look at a generalized M1 energy level diagram for a molecule, we find that they are the typical energy levels there. We got a sigma bonding, pi bonding, and that is non-bonding, pi star, that is anti-bonding pi orbitals, and sigma star, that is anti-bonding sigma orbitals there. And this is a typical energy level kind of sequencing there. That is an energy level kind of ordering over there. And the possible transitions happen to be the 6 of them as shown over here. You can have n to pi star transition, pi to pi star, n to sigma star, pi to sigma star, sigma to pi star or sigma to sigma star. and depending on what is energy involved in that, you get this location of these transitions to be at different places there. Out of these possible 6 transitions, we find that typically in any molecule, one more thing which probably we need to be brought in over here is, that is, when a molecule is there, the different molecular orbitals are there and all the electrons are filled into these molecular orbitals. So, the one orbital which is highest occupied molecular orbital, that is called as HOMO. The transition typically occurs from this HOMO level to lowest unoccupied molecular orbital. So, HOMO to LUMO is the transition which is taking place when you talk about the electronic spectrum there. And all these 6 transitions are shown over there. Only n to pi star and pi to pi star are the ones which can be achieved by the energies available in the UV visible region. That is where we do our electronic spectroscopy there. So, the possibilities are there, sigma to sigma star is there, but that will not be observed if I am using UV visible radiation as a source of radiation there. Okay. So, and generally out of these 2 kind of transitions, pi to pi star transitions are of more intense as compared to n to pi star transitions, which are relatively weaker in that. Okay. So, that is a little thing which we wanted to bring in to just to complete our argument about electron spectroscopy. Okay. Let us sum up what we have done today. What we have done today is, we briefly reviewed the contents of the previous session. Thereafter, we discussed the factors which determine the intensities of electronic spectral states. Thereafter, we brought in Frank quantum principle and discussed its significance. We defined what it is, what does it mean, what does it signify. Having done that, we discussed the possible types of spectra, what we can obtain depending on the basis of Frank quantum principle for different kind of arrangements of the energy levels, the ground state energy level and the excited state energy levels there in different kind of molecules. Thereafter, we defined what do we understand by dissociation energy and explain its determination from the spectrum in different cases, depending on what are the internuclear distances between the ground state and the excited state. Thereafter, we recalled the formation of sigma, pi and molecular orbitals, and with that we just generalized M1 energy level diagram and showed that what are the possible transitions, and out of those transitions, what are the transitions typically observed in an electronic spectrum of a molecule for that matter. With that, we come to the conclusion of our discussion on electron spectroscopy, and also this unitron spectroscopy is complete with this session today. And in the future sessions, we will talk about some other units of the course, maybe a photochemistry will begin with that. Thank you so much.